Basic question. Question A. Display the data using a histogram. Describe the distribution of calcium intakes for these women. So on the screen right now there is a histogram of the calcium labeled at the bottom and then the number of temps labeled on the left side. And as you can see, it's skewed to the right. The spread was really large. It was 2,059 milligrams between each of them, which is 374 to 2433. The median or center value was 854 milligrams, which is very strongly skewed to the right, and there's potential outliers at 2,433 milligrams and 1,933 milligrams. Part B, calculate the mean, the standard deviation, and the standard error. So to do this, you put it all into your list on your calculator, and then you get the one variable statistics, and the mean was 926 milligrams, standard deviation was 427, and then to do the standard error, you do the standard deviation over the square root of the amount of samples you have, and that equaled 427 over the square root of 38, and that equaled 69.27 milligrams. Part C, find a 95% confidence interval for the mean. So a confidence interval means to do PANTS. So the parameter was daily calcium intakes for women aged 18 to 24. The assumptions, we can assume that it's a random sample. We can assume independence. It's very skewed to the right. N is greater than 30, and so we can proceed. Then for N, it's a confidence interval t-test, which means the mean plus or minus t star standard deviation over n. And so x equaled, or the mean equaled 926 milligrams. The t star equaled, which you find in your charts in your book, equaled 2.042. And the standard deviation is 427, and n equaled 38. So then t was 926 plus or minus 2.042 times 427 over the square root of 38, which gave you 926 plus 141.45 and 926 minus 141.45, and that equaled 1067.45 and 784.55. So we can be 95% confident that the calcium intake for women is between 784.55 milligrams to 1067 milligrams. Part D. Eliminate the two largest values and recompute the 95% confidence interval. What do you notice? So after taking out the two largest values, you do the same exact formula, which is the mean plus or minus t star times s over the square root of n. And the new mean, which all you do is you go into your chart and then you just take out the two largest ones and then you get the one variable statistics again. And so the mean equaled 856 milligrams, t star equaled the same, and the standard deviation is 307 milligrams. So that gets you 856 plus or minus 2.042 times 307 over the square root of 36. So then that gets you 856 plus 104.48 and 856 minus 104.48, which equaled 960.48 and 751.52. So the interval got smaller between the data. This shows that the two larger values were outliers and that the data is skewed to the right. Advanced question. Question A. Are the two games independent? Explain. They are not independent. If you win one game, you are less likely of winning the second one, so therefore that proves it's not independent and that it doesn't just revolve around itself without anything outside of it affecting it. Probability that you lose both games. So, I drew a tree chart in the box, and I showed the first game and the second game. So you have a 0.4 probability of winning and a 0.6 probability of losing the first game, and then the second game you have a 0.2% chance to win and a 0.8% chance to lose. And then the second game, if you lose the first one, is 0.3 to win and 0.7 to lose. So then what you do is you do the probability of A and B And so you do zero point 0.6 times 0.7 is equal to 0.42, and so there's a 42% chance that you would lose both games. Part C, the probability you win both games. So to get that, you do the probability of A and B again, and this time it'll be zero point 0.4 times zero point 0.2, which is equal to 0.08, and so you'd have an 8% chance of winning both games, which is not very high. Part D, let random variable x be the number of games you win. Construct the probability model for x. So the probability of losing both is 0.6 times 0.7, which is equal to 0.42. The probability you win one and then lose one is 0.4 times 0.8, which is equal to 0.18, and then 0.6 times 0.3, which is equal to 0.32, and then you would add those probabilities, and that equals 0.5. And then the probability you win both is 0.4 times 0.2, which is equal to 0.08. And so at the bottom, I show the chart, and there you go. Part E, what is the expected value in standard deviation? So the expected value is E times X is equal to N star P. And so that is equal to 0 times 0.42 plus 1 times 0.5 plus 2 times 0.08, which is equal to 0.66. And so the standard deviation is the square root of 0.66 squared times 0.42 plus 1 minus 0.66 squared times 0.5 plus 2 minus 0.66 squared times 0.08, which is equal to 0.62. AP question. So the AP question asks, is there a significant difference in the mean amount of E. coli bacteria detected by the two methods for this type of beef? Provide a statistical justification to support your answer. So anytime it asks to do that, you have to do phantoms. And so our parameter is the levels of E. coli and the different kinds of beef. Our hypothesis, our HO is UD is equal to 0, and our HA is UD is not equal to 0. So our assumptions, we can assume independence, assume normality, and n is greater than or equal to 10, so we just have to proceed with caution. Our n is a paired t-test, and that is equal to, t is equal to the mean times d minus 0 over the standard deviation over the square root of nd. So then you need to find our degree of freedoms, and that's 10 minus 1 is equal to 9. And so our alpha value is equal to 0.05. And then t. T is equal to 0.29 minus 0 over 0.629727 over the square root of 10. So t is equal to 1.46, and our p value is equal to 0.1793. O. 0.1793 is greater than our alpha value of 0.05. So M, make our prediction. We fail to reject the HO. S, we fail to reject our HO that the MD is equal to 0 because our P value is 0.1793. This is above our A value of 0.05. Therefore, we do not have enough evidence to claim there's a difference in the levels of E. coli in these meats.